on Canvas finally that we will in fact push the midterm to the Friday after this one. Okay, so we'll start the midterm on November 5th in class.
I think the 5th is a Tuesday.
Really? I thought, so the 31st is a Sunday, right?
Yeah. Wait,
And then Monday is the 1st.
it's a Friday.
Yeah, November 5th is
The second's the Tuesday.
yeah, November 5th is a Friday. Okay, so do 11:05 in class. And I'm halfway done putting together a practice midterm. I'll send that out this evening. Okay? Practice midterm. Out tonight. Okay. So, right. Before we resume our conversation about contours, and then we'll begin to talk about contour integrals today. Did anybody think about that problem I posed to you about trying to take a branch cut that was not just a ray? What do we think about that? Anything useful or interesting? Nothing in particular. Okay. Well, in that case, maybe I'll just write down whatever I think about it and send it out to you all. Yeah. Basically, my basic thought is that you have to make tau, your choice of branch for the argument, depend on points that lie along that curve, the upper half sideways parabola, y equals root x. Okay. And then there's a little bit of work to do that you can show that log with that definition of R, that choice of branch of R is in fact analytic in the resulting domain. Yeah, maybe I'll just say something about that a little bit later. It's not all that important, I just think it's kind of interesting. Okay, so anyway, we defined a contour at the end of Friday, right? As just a concatenation of a finite sequence of directed smooth curves, right, that are compatible. That is to say, the direction of one piece matches the direction of the next piece, and so on and so forth, right? So that you can, a contour has a direction in its own right. You have to be able to piece together each directed smooth curve to get the total capital gamma, right? The contour. Okay, so what's going to be most important to us is to be able to parameterize contours, right? This is going to be instrumental to how we calculate contour integrals, right? We'll show that the integrals are in fact independent of the curve that we choose between 2 points under the right condition, but choosing a parameterization gives us the ability to state something similar to the fundamental theorem of calculus. Okay? And again, we'll state that that is in fact independent of the parameterization we choose, but in order to actually use the theorem, we have to come up with some parameterization. So we should practice this, I suppose. Okay, so
Pencil your borrow. I'm already my
okay. Let me ask you to parameterize the contour gamma, which I'll say has three directed smooth curve components, gamma 1, gamma 2, and gamma 3, shown below. For t between 0 and 1. And let me draw you this picture. Okay, so I'll take my real and imaginary coordinate axes, and first I'll say that my first directed smooth curve is this line segment, gamma 1. So this is complex number 0. And here we have the complex number 1. Then let us go here. Here's our second directed smooth curve, which is just a line segment from the complex number 1 to the complex number I. And our third directed smooth curve will just be this line segment from I back to 0. Okay, so what do I mean by a parameterization of capital gamma? I mean a parameterization of each of these three components that fit together in the right way. Okay, so how do I parameterize a line? Anybody remember this from?
Yeah, you have point plus the parameter times the direction vector.
Yeah, that's correct. But let me just write that in a slightly different way. This is to say, I want to take my, so for example, gamma 1, let me parameterize as z1 of t is equal to my initial point times 1 minus t. Sorry, 1 minus t. Plus my final point times t. Right? So think of what happens. Of course, here I'm just taking a kind of a standard construction for a line. I'll start by doing a naive thing and just parameterizing each line segment from 0 to 1. And then I'll change the domains of each parameterization so that I get a parameterization of capital gamma that runs from 0 to 1. That is to say, I have to chop up the domains or restrict the domains so that the first third of my time traverses gamma 1, little gamma 1, the second third, little gamma 2, and the final third, little gamma 3.
How do we know what's in thirds?
It doesn't have to be in thirds, right? As long as I cut up my interval 0 to 1 into 3 pieces, okay? It's just kind of natural to choose thirds. You don't have to, of course. Okay, yeah, that's the thing. Parameterizations are highly non-unique, and there's many ways to parameterize a given curve. And in fact, you can parameterize curves which look smooth in non-smooth ways, right? But all it takes for a parameterized curve to be smooth is that there exists some parameterization which is continuously differentiable and satisfies all these conditions that we wrote down on Friday, right? Okay, so I'm going to start naively and say that each of my parameterizations goes from 0 to 1. So I like to write this way because it's kind of natural to see what's going on, right? At t equals 0, at my initial point, I start at my initial time, I start at my initial point, right? And I from my final point. And then as I move in time up to 1, I get closer and closer to this being 0 and this being 1. Okay? So, of course, what you said is also correct. I just think that this is a good trick to remember how to easily parameterize a line. Okay? Okay, so similarly, we can very easily come up with parameterizations for our other 3 line segments, right? My initial point here is 1 minus t plus I times t, which all together gives me 1 minus I minus 1 times t. Okay? And z3 of t,
Can you explain why you could do the initial point 1 minus t plus?
yeah, right. So again, think of what happens at t equals 0. I just get back my initial point. And then as I move in time, as I become closer to 1, I get less and less contribution from my initial point and more contribution from my final point to determine what the complex number is that I get to. Okay? Okay, so my initial point here is 1 minus t plus 0 times t. Okay, so yeah, I minus I t. Okay, so these are each of the contours, gamma 1, gamma 2, and gamma 3, parameterized separately. And what I'm looking for is a parameterization of capital gamma, where my domain is from 0 to 1, so I just have to, in some fashion, break up the interval 0 to 1 into 3 pieces, where I traverse each of these things. And just because it looks nice, I'll do a third of the time per piece. As you were saying, it doesn't really matter what we choose to break it up, but again, just somewhat natural, I suppose. So I should say changing rates at which each gamma I is traversed yields z1 of t, now we'll say instead, is 3t for the time interval between 0 and t is equal to 1/3. Okay? z2 of t will then just say is 1 plus 3 times t minus 1/3 times I minus 1. Going from 1/3 to 2/3. Yeah? That is to say, my start time is 1/3, that gives me a 0 here. I'm going at a third the rate, so I multiply by 3. Okay. And d3 of t, we just get I minus 3 times t minus 2/3 I for t between 2/3 and 1. each of these equations, right? 3t for t between 0 and 1/3. 1 plus 3 times t minus 1/3 times I minus 1 between 1/3 and 2/3. And finally, I plus 3 times t minus 2/3 I for t between 2/3 and 1. Okay, so in general, parameterizing a curve is quite difficult if we don't know an equation that describes the curve, right? That is to say, if we know that our curve is the graph of some function, it's pretty easy to come up with a parameterization, right? We just set the parameter to the variable, right? But let me say that for our purposes, we'll almost always just be parameterizing line segments and circles. It turns out that suffices to do all the things with complex integration that we want. Almost always. Okay? Well, maybe I'll ask you some challenging problem down the line about having to parameterize some weird curve. But in general, you'll get by just fine knowing how to parameterize line segments and portions of circles. Okay? Okay. So now I know we're still a little bit dry here, but I have to introduce a little bit more terminology before we go on. Okay. So let me just say a piecewise smooth curve is the undirected underlying set of some contour gamma. Okay? So we may often or sometimes have occasion to talk about gamma without a direction. Okay? So let me also say, if we parameterize a contour gamma backward, we call the resulting contour the opposite of gamma.
The undirected set of gamma?
Oh, the undirected underlying set of gamma.
Oh,
Right, so, you know, gamma, I insisted had some direction. So really, I just mean to say, like, forget the direction of gamma. That's called a piecewise smooth curve. It's called the opposite curve. Sorry, opposite contour. Of gamma denoted negative gamma. Okay. Furthermore, a closed contour, I bet you can guess what this is. or loop, we'll sometimes use as terminology, is one with the same initial and terminal points. Okay. And furthermore, a simple closed contour. Is one which is 1-to-1 at points other than initial and terminal. What am I saying here? I.e., no self-intersection. Other than where they meet again, where the contour meets itself again at that one point to close up. Okay? Okay. So, here's the important theorem that will actually underpin a lot of the work we do in the next few chapters, which I mentioned on Friday, the Jordan curve theorem. Which says that any simple closed contour gamma separates C into two domains. Here I use domain in the topological sense, right? A open and connected set of C, right? Two domains. Two domains, each with boundary gamma. A bounded one, the interior, and an unbounded one, the exterior. Okay, so that is to say, let's pretend my chalkboard is a complex plane. Okay, here I have the interior. Here's my simple closed contour gamma. It's just a circle. Here's the interior, the bounded portion, and everything outside that is the exterior. Okay. This is a very challenging theorem to prove. It requires a lot of topology. And I think I mentioned on Friday that it actually holds in much greater generality than this. Right? It turns out that any simple closed curve, that is to say, we've already made this definition of contour to be a finite sequence of smooth curves, right? Concatenated. This Jordan curve theorem holds for an arbitrary closed curve, right? I started to draw you this Koch's snowflake, right? This is not a smooth curve, but it still separates the plane into two domains, right? An interior and an exterior. And in fact, you can generalize this to say that any closed curve, not even simple, separates the plane into as many regions plus one as number of self-intersections it has. Right? So, for example, here's a closed curve that has one self-intersection, and here's 1, 2, 3 regions that it separates the plane into. Okay, so proving this in full generality is quite difficult. So, Jordan curve theorem, very hard. Proof. But say if you're interested, a good reference is, I think you can probably find this online without too much difficulty. Check Mungre's topology. Okay. That's where I think the first time I saw this was. I think the exposition is pretty good and doesn't require that much background. So if you're interested in the proof of this, take a look here, but we're not going to do it. I don't expect you to have to know all the topology required here. Okay, so one final piece of terminology for now. I just want to say what sorry, I should say a simple closed contour gamma is positively oriented if the curling right-hand rule results in your thumb pointing toward you. Right, so we talked about this on Friday as well. This is the analog of going clockwise, or sorry, counterclockwise. Right, just curl your fingers in the direction that the arrow points, and if your thumb points out at you, then it's called positive. We just make that designation arbitrarily then. So this is positively oriented. Clockwise. And as you can guess, otherwise, negatively. Okay. Clockwise. Okay. If I curl my fingers the way the arrow points, my thumb points into the board or away from me if I'm like looking at a piece of paper and it goes in. Okay, Right. So now let me just remind you of a formula from single variable calculus. Or perhaps maybe you encountered this in multivariable calculus, but it applies equally well to a function of a single variable. See, I think you probably saw a version of this in calculus 1 or 2. But let me remind you. And we'll just state it as a definition. Okay, so given a smooth curve, gamma with parameterization z of t is equal to x of t plus I y of t, where our domain of parameterization is the interval a to b. And we'll say s of t, the arc length of gamma traversed, I shouldn't say at, traversed from A, or rather I should say Z of A to Z of T, then from real calculus, recall that we can derive the formula ds dt is equal to the square root of dx dt squared plus dy dt squared, which we can just rephrase as the modulus of the derivative of our parameterization. Okay, right, and I think you can probably remember this, and it's probably not too hard to derive again, but again, we'll forego that for now. Then the length of gamma is given by, we'll denote it L of gamma, which is a funny notation because it looks like an upside down gamma and a right side up gamma, is just equal to the integral from A to B of ds dt, or if you prefer, sorry, I should be a little bit more precise here, with respect to t, or the integral from A to B of the modulus of dz dt with respect to t, which is independent of the parameterization. Independent of parameterization. accordingly, we have an analogous notion of what the length of a smooth contour is. Accordingly, the length of a contour, capital gamma. I guess I should write specifically, this is 1, gamma 2, up through gamma n, is given as just the sum of the length of the components. L of capital gamma, not F, sorry, capital gamma is equal to the length of the smooth curve gamma 1 plus the length of the smooth curve gamma 2 all the way up through the length of the smooth curve gamma n. Okay, so this is just a lot of terminology and machinery that we'll now use to define the integral of a complex function along a contour. Okay, so why do we go to this trouble? Well, remember, since we're in the complex plane now, is the domain of some function we might want to integrate. It's not so easy to determine what our bounds of integration should be, right? When we're dealing with real functions, we only have to decide what interval we're integrating over, right? But now, if we want to do an analogous type of integral, we could take any path in the plane and try to integrate along that. So we want to be precise about the way that we do that. And in fact, what we'll do to build that up is discuss what it means first to integrate a complex function over a real interval, and then kind of build from there, right? Because a real interval in the complex plane is just a special type of smooth curve, right? Yeah.
So just a question about it's independent of the parameterization. Does that mean if you have like a parameterization for gamma in terms of uppercase gamma, gamma 1, gamma 2, gamma, etc. If you change one of the parameterizations of one gamma sub n, will that affect the arc length, or is that completely independent?
It's independent. It's independent for each of these.
Yeah, so each one of those is independent.
Yeah. Right. So yeah, this is to say the length of a smooth curve is independent of the parameterization, which shows us that then each of these summands is independent from the parameterization, which makes this also independent of the parameterization. And that goes back to, that's consistent with what we said a parameterization for capital gamma was. It's just a choice of parameterization for each of the components, gamma 1 through gamma n. Yeah. Good?
Yeah.
Great. Okay, okay, so contour integrals. So first, a very brief review of Riemann sums. Okay, remember we define real integrals in terms of Riemann sums, which depend on quite a bit of machinery in their own right. But if we want to be at least somewhat precise of how we construct these integrals over an arbitrary contour in the complex plane, it's worth revisiting the basic definitions. We won't go all the way into the proofs of everything using Riemann sums. That's tedious, and I'm confident that if you really wanted to, each of you could reproduce that yourselves. I think that would be not a good use of class time. But it's helpful to just remember the definitions, because the things that we'll define go down to those. They depend on those things. Okay? Okay, so, so here's the first important point. Given a directed smooth curve, gamma, from point alpha to point beta, we can, this is kind of interesting, but hopefully obvious when you think about it. We can order the complex numbers lying on gamma, I'm sorry, lowercase gamma, okay, so this is in contrast. If you remember at the beginning of the term we said there's no way to put an order on the complex numbers. You all proved that in the homework, right? However, when we take a smooth directed curve, there is a natural way to order that subset of the complex numbers. Okay? So where does this come from? So what we do is we think of this as gamma inheriting the order imposed by some parameterization. That is to say, wait, I really should say by the domain of some parameterization. Let's say Z is some parameterization which has domain in the interval A to B. Okay, so we'll say Z parameterizes gamma. Then what we say is that, what should I say here? Let's see. Yeah, let's say alpha 1 and alpha 2 on the curve gamma, then alpha 1 is strictly less than alpha 2 if and only if T1 is strictly less than T2, where Z of T1 is equal to alpha 1 and Z of T2 is equal to alpha 2, right? These T1 and T2 are in the interval A to B, right? And we know that the real numbers have a strict ordering, right? So we just say, because of the conditions we imposed on what a parameterization is, that it's one-to-one for a smooth directed curve, right? This allows us to unambiguously define this order relation on this subset of the complex numbers. Okay? So we're being a little tricky here, right? Even though there's no order on the complex numbers, for this subset, for this particular integration that we'll define, per parameterization, we'll define an order. Yeah?
The order is basically just the order that the parameterization arrives at each of the complex numbers.
Precisely. Yeah. Good. some of the machinery to define Riemann sums. Okay, so for positive integer n, remember that we define a partition this script p sub n of gamma to be a finite collection of points z naught, which we'll insist is equal to alpha, or if we have a particular parameterization, like in the setup here, we'll say that alpha is our initial point of our smooth directed curve gamma, and so that happens at the beginning of our parameterization, z of a. Okay, so we get this finite collection of points, z naught, z1, z2, z n minus 1, and then we insist that we end at the end point of our smooth curve gamma, or directed smooth curve gamma. Satisfying z sub k minus 1 is less than zk for k between 0 and n, right? And notice I'm comparing these complex numbers by this order relation that I just defined. Okay? They happen, each of these finite points happens earlier in the parameterization of gamma than the next one down the line. Okay?
Can you have k equals 0? Like,
Can I have k equals 0? No. Right, sorry. Since I defined it this way.
okay.
Yeah, you're right. There's no such thing as k. Z sub -1, right? Good, thank you. Okay, so just here's our contour gamma. Here's alpha. Here's beta. And all I'm saying is I'm cutting up my curve into some segments, right? Just breaking it into little pieces. So I read some of you actually filled out that middle term survey that I sent out, and there was a pretty good suggestion that we should take a break at 50 minutes. So why don't we just take a 5-minute break and reconvene at 2:30. And then we'll talk more about the machinery behind Riemann sums in this context. And this will be a regular thing from now. We'll just take a 5-minute break in the middle.
homework, yeah.
Okay, no.
I was getting water. Good in class.
So how similar is a practice exam gonna be to the regular exam?
It'll be the same difficulty and the same length.
Yeah, okay.
Yeah. That's why it's kind of taken me so long to get it together, because I was trying to amass enough problems that were similar enough to one another that I could produce essentially 2 exams.
Gotcha.
But yeah, it'll be designed to take the course period, maybe slightly less. I'm thinking like between 5 and 6 problems. Definitely less time consuming than any of the homework.
Can we expect the exam to be like more computational than proofs and whatnot, or?
There'll be a mix.
Yeah, okay.
You might have to prove some simpler things than anything I ask you to prove on the homework. And yeah, there'll be some computations as well.
Will there be like a calculator or anything?
No, you won't need a calculator, and I don't think there's really any super important formulas that you shouldn't remember. Right? Like, you should know the Cauchy-Riemann equations, because it's laborious to look them up every time, and they're not that hard to remember. They're easy to confuse, but they're not that hard to remember.
Or rederive.
Or rederive, even. Yeah, you might say that. Right. Yeah. Just keep a analytic function in mind, and just check which way the relationship goes between the partial derivatives of the components. Okay. So let's continue with our discussion of Riemann sums. Okay. So here's the distinguishing feature of a partition. The mesh of a partition piece of n is the largest arc length of gamma on interval z sub k minus 1 to z sub k, which we denote mu of p sub n. So the thing that this is keeping track of is, if think of this, if mu of p sub n is small, the partition of gamma is finer. That is to say, the maximum length of the distance between any of our 2 points, our adjacent points, if that's small, then all the other ones must be smaller, right? And our curve gamma must be more subdivided, right? So we're kind of keeping track of how subdivided, in some sense, gamma is by just looking at the largest piece of arc length. Okay? Okay, so now let's let C1 up through Cn be again points on gamma satisfying Ck is an element of z k minus 1 to zk. And set delta zk is equal to the difference of zk minus zk minus 1. So, again, this is some approximation of the arc length of each subinterval, right? So, and we have, for example, this is delta z2. This is a little line segment. And as we become more subdivided, each of those line segments makes a better approximation of our chunks of gamma, right? Okay?
Just a quick question.
Yeah.
The mesh. Can the mesh, is it necessarily larger, or can it be the same?
So the definition of the mesh is that it's the largest piece of
Does that
arc.
mean everything else, like, if every delta z is equal, is the mesh the same mesh?
Yep.
Okay.
Yep. I didn't say it's
Doesn't-
the unique largest. It's just
Okay.
happens to be the largest one.
So the mesh isn't the interval that it's on, it's just the arc length.
Yeah. Right. Is the largest arc length. Yeah, it is the largest arc length. But what are you computing the arc length of each of these intervals?
Right, just like, yes, you feel like 3 arc lengths that are the same length is fine because they're all the mesh.
Yep. The length
Yeah,
is the mesh, right? You get the mesh from each of those 3. Okay. So, then the Riemann sum of some function f, which is defined on our smooth directed curve gamma, corresponding to some partition piece of n, is given as S of p sub n, the sum, or Riemann sum, is just equal to the sum from k equals 1 to n of f evaluated at c sub k times delta Okay, now, if you remember, back when you studied integration at first, this is exactly the same as the definition of a Riemann sum in that setting. The only thing that's different is that we're now secretly depending on this imposed order on our subset of the complex numbers. Okay, and this is built on top of that in a certain sense. Okay, now we can say what it means to be integrable in the complex sense. Okay, so let's let f be a complex function find on gamma a directed smooth curve then we say f is integrable along gamma if there exists a complex number call it L that is the limit of every sequence of Riemann sums S of P sub n corresponding to corresponding to a certain sequence of partitions, or a sequence of partitions that satisfies some condition. Anybody guess what that condition might be? Any sequence of partitions what condition could I impose on a sequence of partitions that would make my sequence of related Riemann sums converge? What are the salient features of a partition? Well, we have the points that we choose, right?
Is it in the limit as the mesh goes to 0?
Yeah, exactly. Any sequence of partitions satisfying that as n goes to infinity, mu of p of n, goes to 0. Okay, so in summary, let me just write this in terms of limits. This is to say, if the limit of the mesh of a sequence of partitions of gamma as n goes to infinity equals 0, this implies that the limit as n goes to infinity of the sequence of related Riemann sums to this sequence of partitions equals L, this complex number. This is quite a powerful statement. right? It's saying that no matter how I break up, how I chop up my curve gamma, if I construct a sequence of Riemann sums, a sequence of partitions where the mesh gets smaller and smaller and smaller, my function is integrable if this related sequence of Riemann sums converge to the same limit for each such sequence of partitions. Okay, so this is actually saying a lot. And it seems like, is any function integrable? I have imposed a lot of conditions here, right? Okay, so we all know the story, right? You make the same type of definition for functions of a real variable, and then it turns out that most all functions are integrable, right? Like, you have to do some work to construct a non-integrable function. Like, you technically don't even have to be continuous. All you need to do is be piecewise continuous. That guarantees integrability, right? So, we'll see a similar story here. Well, it's called the integral of f along gamma and sometimes we just write this. L is equal to the integral along gamma of f dz. Okay, so just if you really look through this definition, you'll see the usual properties of integrals hold. Okay, so what do I mean by this? If I take the integral along gamma of either of the functions f of z plus or minus g of z dz, this is just equal to the sum of the integrals of f along gamma and g along gamma separately. Oh, sorry, plus or minus g of z dz. Right? I can also pull constants out, right? The integral of c times f of z dz along gamma is just equal to c times the integral along gamma of f of z dz. Okay, and I promise that writing concatenations of smooth curves to create contours would provide us some nice notation when we started to integrate along contours. Well, here's the first step in making that arithmetic nice. We also have the property of integrals that if I integrate along the opposite of the smooth curve gamma, the smooth directed curve gamma, the function f of z dz, I get negative of the integral along gamma of f of z dz. Okay, so this is kind of why we set up this additive notation for how we construct contours and how we can concatenate smooth directed curves. Okay, so right now, here's the analog of what we've seen before in real calculus. If f is continuous, some smooth directed curve gamma, then f is integrable along gamma. Okay, so this is the proof of this is not very illuminating, so we're not going to do it. Again, it mirrors exactly the proof from real calculus. So you can go back and look at your old notes or just look it up on the internet. In fact, the book doesn't even do this, but another book you can find online for free pretty easily is Complex Analysis by Lars Alfors, which it's a very complete, rigorous approach. It proves everything. If you're ever curious about a proof that we don't do in class, I'm happy to talk about it, but you could also check there. So let me just say, see Alfors complex analysis. The writing style is quite a bit terser than our textbook, but it is helpful to slog through it if you don't exactly understand something. Okay. So we're not going to prove this, but this is all well and good. And again, I want to draw an analogy with the integration of real functions. We prove the same thing before we have any effective way of actually computing integrals, right? This is to say, all this tells us is that f is continuous, then we know that this limit L exists, right? What we would like is some analog of the fundamental theorem of calculus, which allows us to, once an antiderivative is known, easily compute a given integral, right? But now, of course, again, there's this extra complication that we have this curve, gamma. It's not just an interval. So we have to do some accounting for how gamma moves. That is to say, what the path gamma traces is. Okay? So, let's take some steps to do that, and we'll proceed exactly as I mentioned at the beginning of lecture today. We'll start by looking at what happens when a complex valued function is defined and continuous on a segment, an interval on the real axis first. And then we'll very cleverly try to transform an arbitrary contour integral into one that can be realized as an integral along a chunk of the real axis. Okay? So, here's our theorem. F is a complex valued function continuous on the real interval A to B. And we have some antiderivative of this function for all t in the interval A to B. Then gamma of f of t dt is equal to the integral from a to b of f of t dt is just equal to f of b minus f of a, where gamma is this smooth directed curve in the complex plane, right? That is to say, here's my curve gamma. It's just this chunk of the real axis that I'm going from A to B. Alright, so this kind of points out that this relationship is just like in real calculus. If you switch the limits of integration, you go from positive to negative, right? That would be to say, if I go from A to B, I'm positively oriented. If I go from B to A, I'm negatively oriented, or I'm the opposite orientation of gamma. And that would just give me a negative sign here. Okay? So, here's a quick proof. So, the integral from A to B of f of t dt is just the integral from A to B u of t, I'll put this in square brackets, plus I v of t dt by our usual properties of integral now applied to a complex function, and I just get the integral from A to B of u of t dt plus I times the integral from A to B of v of t dt. Okay? Then we get this is equal to u of b minus u of a plus I times v of b minus v of a, which is equal to u of b plus I v of b minus u of b minus plus I, jeez, I keep screwing this up, sorry. U of a plus I v of a. Okay? F of b minus f of a. Now, of course, since we assumed f continuous on AB, this implies the component functions u and v continuous on AB, which for real functions we know implies integrable. With antiderivatives, again, notice here that there's no requirement of analyticity here for a complex function to be integrable. So we're not saying anything about how u or v or capital V or capital V are behaving with respect to differentiation, except for that capital U and capital V are differentiable and their derivatives equal u and v, the components of little f. Okay, so this just follows basically straight up from what we know about integration of real functions. Just looking at this component-wise. Okay, so really quickly, let me ask you to compute the integral from 0 to pi of e to the I t dt. Okay, I have some complex function that I'm integrating on a real interval. So I'm just looking at this real variable. And furthermore, I know that e to the it is continuous everywhere, right? I actually know that e to the it is analytic everywhere, so certainly it's continuous. How do I proceed in this problem? I satisfy the hypotheses of my second theorem here, right? So all I need is some antiderivative of this function e to the it.
1 over I e to the it.
Yeah, it's just a u substitution, if you like. Right? It works just the same. Since we know how differentiation of e to the z works in general, and that the chain rule applies to complex functions. Okay, so this is just equal to e to the it divided by I, evaluated at pi and 0. So we get e to the I pi divided by I minus e to the I 0 divided by I. Okay, so what's e to the I pi?
-1.
-1. And what's e to the 0?
1.
Yep. So altogether, we get -2 divided by I, or if we like, we can quote rationalize the denominators and get 2i. Okay. So just kind of like what you'd expect. Integrating complex functions is along a segment of the real axis is no harder than integrating real functions, as long as we know an antiderivative, which, we have a decent vocabulary of those functions now, right? We know how to anti-differentiate polynomials and the complex trig functions.
If we really wanted to or needed to, we could break down e to the it into like cosine and sine and then use what we did in the proof to go all the way through.
Sure, yeah, that would result in the same answer. Yeah.
Is it ever helpful to do something like that?
Yes, it may well be. Yeah, you might be able to see things more clearly if you break things into a component form. It's a good observation. Yeah, if you ever get stuck, if you're like, okay, well, I know abstractly that this complex function is continuous, but I'm having a hard time finding an explicit antiderivative, it's worthwhile to look at the components and see if that sheds any light on the situation. Yeah, good. Okay, so now let's look at the case where gamma is any directed smooth curve along which f is continuous. So now assume gamma is any directed smooth curve along which continuous. Okay, and let's choose a parameterization of gamma. Of gamma. Z of t on the interval a to b that agrees with the direction of gamma. What do I mean by that? I mean that T naught is less than T1 if and only if Z of T naught happens before, in the parameterization, Z of T1. Okay? Then, for any partition Pn of, oh sorry, I guess I should give this a specific name. Pn, we'll say is Z naught, Z1, Z1, up through Zn of gamma. We can write Z naught is equal to Z of A, Z1 is Z of T1 for some T1 in our domain of parameterization. Z sub n minus 1 is equal to Z of T sub n minus 1. And Z n is equal to Z of B. Or A we'll call T naught strictly less than 1, strictly less than T2, Tn minus 1, strictly less than Tn, which we're just letting equal to B. Okay. Recall our stipulations on a smooth directed curve tell us what? That there exists some parameterization Z for gamma that has a continuous derivative, right? Yeah, tell us. There is parameterizing gamma with parameterization satisfies this. Right? I gave you some parameterization. Now let's indeed insist that whatever parameterization we choose has continuous derivative. Right? This is what I was saying sometime near the beginning of class today, right? Parameterizations are non-unique, and in fact, there are non-smooth ways to parameterize smooth directed curves. What's important is that there exists some smooth, that is to say, having continuous derivative parameterization. So we're just going to ensure that we pick one such parameterization that has continuous derivative. Okay? So, what this tells us, this implies that the finite difference, that is delta z sub k, which you'll remember is z of t sub k minus z of t sub k minus 1, right? Remember, I defined this delta z sub k in terms of some partition, and I'm constructing my partition based on my parameterization, right? Okay, so I'm looking at this delta z sub k in terms of my parameterization, which I insist has continuous derivative. This delta z sub k can be approximated by the derivative of z at t sub k, times t sub k minus t sub k minus 1. Right? This is to say, when I take the limit of the ratio of this by this, I get the derivative, but I can approximate it by just looking at the actual differences at this finite step, tk to tk minus 1, or tk minus 1 to tk. Okay? So, this in turn implies the Riemann sum along gamma corresponding to the partition that we chose over there, p sub n, of our function f is approximated by the sum from k equals 1 to n of, so this is just the Riemann sum straight up, right? F of z of t sub k times delta z sub k. If I just replace each term in this sum by my approximation of delta z sub k, what do I get? Again, sum from k equals 1 to n of f of z of t sub k times z prime of t sub k times t sub k minus t sub k minus 1. Okay? Now, take a close look at this approximation. This approximation is a Riemann sum of the function f of z of t times z prime of t on a real interval. Okay? All my t's, my delta z's now have been translated down to the real axis. The right-hand side is a Riemann sum for the function f of z of t times z prime of t on real interval a to b. So, without actually proving anything, when I take the limit as n goes to infinity for this whole mesh situation that I set up before, I get that the integral of f of z of t along gamma is equal to the integral of f of z of t times z prime of t from a to b. I've essentially demonstrated that, in fact, I can take an arbitrary contour that I am integrable along and translate that down to a segment of the real axis. Okay? So,
That's just analogous to a line integral, right?
yeah, exactly. Right, but of course, now we're in the complex plane
Yeah, no,
and dealing with complex functions, but it's exactly the same definition.
the same idea.
Same idea behind it, but what's surprising is that when we study line integrals for analytic functions, we can essentially determine the integrals by just the values of the functions at certain points.
Like a conservative vector field kind of.
There is a relationship there. Yeah. Yes.
This doesn't imply that any closed contour would be zero, right, the integral?
So there is something to say about that. We'll say it on Friday. Think about it before then. Okay, that's our time for today. Don't forget to give me your homework. And like I said at the beginning, I'll do my very best to give you that practice exam tonight. But of course, you'll have more than a week to work on it, no matter what.
I submitted it online. I'll try to get it later one next week. But
Oh no, it's really fine if you submit your work online. I don't mind.
I
That's
just
fine.
had it from the past year and a half, I guess.
Yeah, that's okay. I don't mind that.
have a good one for this.
Yep, you do. See you guys Friday.
I finally got saved there.
Oh, great.
But cause I'm like thinking about projected to the.
Thank you.
Yeah.
Can you like first? Here, it's closer.
I'm just folding this, I'm on the stand by, I'm
Oh,
sorry.
that's okay. Don't worry about it.
If it was here and here, you'd do like that, but if you do that stuff, it wouldn't change.
Yeah.
Is that something to do with like, you know, in Calc 3, you have like conservative closed integrals if you draw? That kind of related.
Yeah, so all you need is continuity in some domain that contains the contour, the closed contour that you consider.
Continuity.
Yeah, so in other words, if you take this picture that you just had, right, with
Yep.
something, and let's say my function is just continuous here, then as I traverse, I go outside the domain of continuity, so my integral won't be defined there necessarily.
Yeah.
It might be, but it might not be. So that's, there, like I said, there's some odd condition, I have to say,
Yeah.
extra. But yeah, the spirit of the thing is right.
Huh. Interesting.
Mine's in your office.
Okay, great, thanks. Have a good afternoon.